Okay, so this video is going to be a fairly short one. I'm going to be talking about class amplifiers. All right. Now, the amplifier that we have seen, the common emitter that we have seen, is known as a Class A amplifier. All right, so it's a Class A amplifier. Let me just write down. And what does Class A amplifier means? Well, it really means one thing. It's almost like this is a grade, okay? It's the best amplifier you can have. It's as good as it gets. Now, the problem with Class A amplifiers is that the transistor is on all times, at all times. Whether there's an input signal or not, it still is consuming power because of the DC bias. So the transistor is always on. And because of this, the efficiency, and the efficiency is a percentage, and we define efficiency of a system as what you get, the power that you get at the output over the power that you get at the input, and it's a percentage times 100%. And for Class A amplifiers, the ones, at least the ones that we've seen in class, the efficiency never ever exceeds basically 30%. It's always less than 30%. In fact, in most of the time, it's even less than that. It's around 20%. So what does it mean, an efficiency of around 20%? It simply means that for every 5 watts that your amplifier consumes, only 1 watt is basically comes out at the output. So 4 watts are simply wasted. And we can easily basically understand why is it that way. And let me, by the way, draw a common emitter amplifier. All right, so we've done this one quite a few times in class. So this is the resistor that goes to the collector. There's typically a resistor in here that improves the performance, but we don't want this resistor to be here in AC, so we decouple it with a capacitor. So in AC, this RE basically disappears. And this is our voltage divider that allows us to apply a voltage high enough at the base that will turn on our transistor. So the main point behind this voltage divider, R1 and R2, is simply to make sure that VBE is at 0.7 volts so that the transistor is on all the time. Now, typically, we apply here through a capacitor. All right, so this is a coupling capacitor. This one is a bypass capacitor, so I'm going to call it CB. And this is a coupling capacitor. I'm going to call it C1. And here's my AC signal that I'm applying at the input. All right, so there's an AC signal in here. We're going to call it VIN. And whether VIN exists or not doesn't really matter. There's always a small current, IB, going in here, DC current. And there is an IC. And then eventually IB and IC combine to give me IE. That's pretty much it. So the transistor is always consuming power, whether there's an AC signal or not. If VIN, for example, is just a flat line, if VIN is something that looks like this over time. So there's nothing at VIN. It is not going up or down. There's nothing to amplify. So this is really what this line really means. VIN is a flat line. The transistor still consumes power. And that is a problem. And this type of transistor, for which the transistor is always on, and is typically in the load line. If you remember, the load line is the line that defines the relationship between IC and VCE at all times. This is VCE, by the way. Let me just make a correction in here on, this is not a current in here. This is a voltage. This is VCE. The load line is always something. There's always a linear relationship between IC and VCE. And we've seen that the best place to actually bias our transistor by choosing appropriately RC, R1, R2, and RE is to simply have the quiescent point right here in the middle. So we have the maximum possible swings up, basically left and right to the quiescent point when we apply an AC signal. Right? So this type of amplifier is simply known as a Class A amplifier. Now, to improve the efficiency, engineers simply created other amplifiers Notably, the Class B amplifier, also known as a push-pull. So this is a Class B amplifier. And the Class B amplifier very, very often is referred to also as a push-pull amplifier. Now, the idea here is to have an amplifier that doesn't consume any DC power when there's no or almost no DC power when there's no AC signal. Okay? Now, the way we build this thing is simply by taking a pair of transistors. One is an NPN transistor, the other one is a PNP transistor. So we take a pair, by the way, this pair of transistors very, very often is known as a complementary pair. Basically, complementary means one complements the other one. It's not complementary. It's not complementary. It's complementary with an E here. And what this means is that one complements the other one. In other words, when one transistor is on, the other one is off, and vice versa. Okay? Now, here's a basic circuit that explains to you how we build this one in here. So I'm going to take an NPN, and if you remember, NPN means that the emitter is the current comes out of the emitter, not pointing in. We're going to connect it here to a positive voltage supply. So I'm going to call this VS plus. So this is a positive voltage supply. And then I'm going to make sure that there's a resistor in here. And the purpose behind this resistor is to ensure that VBE will be equal to 0.7. But it's not always the case. All right. And then underneath it here, and by the way, the output is taken out of the emitter. This is my load resistor, and it connects typically to the ground, RL. And then I have here a PNP transistor. So, I'm sorry, this should not be here. This one is the emitter. So for the first transistor, I'm going to call T1. T1 is an NPN. And then T2, I'm going to call this T2, is a PNP. All right, so I'm going to have here a negative power supply, VS, I'm going to call it minus. I'm going to have here a resistor, I'm going to call it, this resistor we're going to call it RB1. And this one we're going to call it RB2. Or simply R1 and R2, let's call them just R1 and R2. Okay, and then in between these, this is where I inject my signal. This is where the input goes in. Vin. And Vin is basically an AC signal. All right. Now, in between the output and RL, typically we have here actually a capacitor. So I'm going to simply delete area in here and put a capacitor. Okay, so here's my capacitor in here. And both of these capacitors are coupling capacitors, so we're going to call them C1 and C2. All right, well, how does this circuit work? All right, so let's imagine at the beginning that Vin is equal to 0. All right, so we're going to assume that Vin looks something like this. So this is Vin drawn as a function of time. And let's just imagine that Vin is a simple sine wave. All right, nothing really complicated here. This is Vin, and the pattern of Vin repeats over and over again. All right, so let's say at the beginning Vin is equal to 0. All right, this voltage typically in AC is equal to 0 when there's nothing going on. As Vin increases, as long as Vin has not reached 0.7, and this is what this line stands for, this is 0.7 volts. As long as Vin hasn't reached 0.7, what happens is that the voltage here, and we're going to assume that this voltage, in fact, we can remove the capacitor altogether. We're going to assume that this voltage here is 0 volts. So as long as Vin has not reached 0.7 volts, there's not enough here to turn on T1. And obviously, as this voltage becomes more and more positive, the second transistor is turned off. Okay? So there's no current that flows here. All right, so there's no current that should, a current should come from here, go through this transistor, and then go to the ground through R1. All right, I'm going to call this IC. All right, so as long as V in is less than 0.7, if I were to draw V out, and V out is simply RL, this is V out by the way, just so that you would know it. V out is taken across RL. So since there's no current going through the load, that means V out is equal to 0. Right, so I'll just draw here another dashed line. So V out is equal to 0. Now when V in hits 0.7, what happens is that the base emitter of the first transistor is now forward biased. And this transistor now turned on, and there's a current flowing in here. So from this point on, as V in goes up, the current across the load goes up and reaches a maximum and then comes back to 0. Now as the voltage starts coming down, as long as it has not reached minus 0.7, the second transistor is off. But eventually this voltage will drop below 0.7. And since the voltage here is now at 0, it is connected to the ground, by the way, that means the voltage between here and here is, and this is the emitter, by the way, for the second transistor. Now there is a 0.7, all right, so minus 0.7 to be precise. So when we reach minus 0.7, this transistor turns on. So the transistor turns on, and as this transistor turns on, there's a current that flows now from the ground through this transistor to the minus. Remember, current always flows. Oh, by the way, T1 is off now. During this cycle in here, during this cycle, T2 is off. And during this cycle in here, T1, transistor 1, is off. Okay, so there's a current that flows from the ground to the negative because the 0 volt in here and negative voltage, this is larger than the ground, so it flows in this direction. Okay, all right, so for a little while, there's nothing in here. And then as soon as it reaches minus 0.7, this transistor T2 starts conducting, and there's a current flowing in the resistor in the opposite direction that it was flowing in a moment ago. And that's the reason why V out now has become negative. So if I were to draw something a little bit cleaner than what I have over there, here's how V in looks like. And here's how V in varies over time. Let's assume that it's a very simple sine. Doesn't have to be sine, but there's no loss of information if it's not. In essence, there is a zone of V in from minus 0.7 volts to 0.7 volts where both transistors, both T1 and T2 are off. And when they're off, what is the value of V out? So in here, so if I draw a dashed line in here and this is V out, it is equal to 0. All right, and here T1 turns on. So in this cycle, basically in the positive cycle, T1 is on and T2 is off. T1 is the first transistor at the top, the NPN. In this, from here to here, there's nothing. And then the second transistor starts conducting. And then it stops here. So what happens in here? T1 now is off and T2 is on. And the output signal looks kind of weird. This is in reality how the output signal without all of the scribbling that I put in there. So there's nothing until V in exceeds 0.7. There's something. When it drops below 0.7, there's nothing until it becomes minus 0.7. And then T2 conducts. So you can see that this does not really look like a sine wave. There's these areas in here. And these areas in here are simply known as a crossover distortion. What this means is that even though the input is changing during this amount of time, if it's within the range minus 0.7 to 0.7, no matter what variations the input takes, the output simply doesn't follow it. So there's a distortion. There's an area in which the output does not follow the input. And this is V out drawn over time. So there's this annoying crossover distortion. Now, the interesting thing about this type of transistor, and I'll go back to the circuit, this amplifier, is that T1 or T2 will conduct only when there's an input voltage. When there's no input voltage, when there's a zero in here, neither one of them conducts and there's no current that flows. Now, there is a current that flows in here, but no current flows through the two transistors. And if we choose these two resistors large enough, this current that flows in here will not be very, very large. But as long as the input is either zero, less than 0.7 or greater than minus 0.7, neither one of the two transistors do conduct, and there is no current flowing through the transistors. So the transistors do not consume any power unless there's an input signal. This kind of amplifier is known as a Class B amplifier, and sometimes it is also called a push-pull transistor. The reason is very simple. The two transistors are either pushing or pulling, right? So basically they take over. When one turns off, the other one turns on. When one turns on, the other one turns off. But what's annoying about this type of amplifier is this area where the input is changing but the output remains flat. The area where Vn is somewhere is less than 0.7 volts but is greater than minus 0.7 volts. When Vin is within this range, Vout is simply a flat line, and this flat lines that you see in here is known as a crossover distortion. To deal with the crossover distortion, engineers simply invented, oh, I forgot to say one thing. The efficiency of Class B transistors is typically 50%, around 50%. So it's a lot better than, there's still a 50% waste, but there's nothing we can do about that 50% waste. It's that waste that we get through the two resistors and also through the two transistors when they are turned on. But the efficiency is way better than Class A, which I said that practically speaking, it's around 20%, a little bit over 20%. So we pretty much have double the efficiency, which is a great thing actually. So this is Class A and this is for Class B. So this is the efficiency for Class A and this is the efficiency for Class B. Now, if that distortion did not exist in there, it would be a great amplifier. Unfortunately, it's there. And that's the reason why engineers went back to the drawing board and simply invented another breed called Class AB amplifiers. Now, a Class B amplifier is almost like a Class B amplifier with one little detail. That area where Vn is from 0.7 to minus 0.7, when Vn is within that black zone or that dead zone, is simply taken care of completely. And here's the actual circuit, and I'm going to explain to you how it works. So we're going to start with a NPN transistor. We're going to call this transistor T1. All right, this is Vs plus, this is the positive supply. Here's R1. All right, there's the other transistor. Okay, this is a PNP that connects to a negative voltage, Vs minus. All right, so we use a resistor in here, a biasing resistor. Let's call these two resistors R1 and R2. But now here's what we're going to do in here, guys. We're going to put a diode here and another diode here. And now we inject our input signal through a capacitor to this point. So this is a coupling capacitor. and this is my Vin. Now let's say that Vin is simply an AC signal, just a sinusoid. The output is taken exactly out of the point where we had it earlier. So we have a coupling capacitor and there's a resistor. We can remove the coupling capacitor, by the way, in this case, and it wouldn't change much. This is the load and this is our Vout. So Vout is taken from here to here, whereas Vin is taken from the ground to here. Now let's assume that Vin is equal to 0. Oh, by the way, we choose these two diodes. We're going to call them D1 and D2. So there's T1, T2, D1, and D2. We're going to choose them so that they are always on, no matter what value is in Vin. So let me put it here as a note. So R1, R2, T1, T2, D1, and D2 are all chosen in such a way that D1 and D2 are always, no exception, forward biased, no matter what Vin is. Now this is very important. All right. So I'm framing this. It's really important to choose the different resistors, the transistors themselves, and the diodes so that they are always forward biased, no matter what value Vin takes. So let me come back in here and then explain how things work. Okay. All right. So when Vin is equal to 0, let's just assume that this is Vin. Right, Vin is a sine wave, so it does something like this. This is not the best sine wave you've ever seen, but it'll do. So when Vin is here, when Vin is equal to 0, all right, what voltage do I get in here? Well, this one is forward biased. That means the voltage at B1, let's call it VB1, the voltage at B1 is 0.7 volts over Vin. Okay, so the voltage here is 0.7 volts over here. And we can assume that, let's just say that this is just a wire. All right, let's just delete that capacitor altogether. We don't even need it. All right, so I'm going to delete that capacitor and just put a wire. All right. Okay, let's come back and just tie a wire in here. So let's just say that the voltage here is 0 volts. Okay, and Vin also is at 0 volts. We are at this point here. Right? So we are here. So Vin is 0 volts. Vout is 0 volts. So that means the emitter voltage, the voltage at the emitter of T1, so VE1 is also 0 volts. VB1 is at 0.7 volts. Right, over VE1, because this diode is forward biased. That means there's a 0.7 in here. That means VB1 or VB1 minus VE1 is 0.7 volts. The voltage between here and here is 0.7 volts. Now you might be wondering, why do I have 0.7 volts? Well, the reason is very simple. I have 0 volts in here. I have 0 volts in here, and since this circuit here, these two resistors, R1, R2, D1, and D2, will ensure that both of these diodes are forward biased. This voltage here is 0 volts, and since this diode is forward biased, that means the voltage across the diode is 0.7. There's a 0 volt in here, there's a 0 volt in here, and 0.7 here in relationship to the 0. That means I have 0.7 in here, which means that T1 is turned on. All right, and if T1 is turned on, that means it will conduct current, and there will be current that flows this way and drains through R1 to the ground. So now we don't have to wait for Vin to reach 0.7 volts. The forward biased diode will raise whatever VB1 is Let me just write down the relationship in here. The voltage at B1 is always Vin plus 0.7 volts. So the voltage at the base of the first transistor is always the input voltage that has been raised by 0.7. So from the get-go, from the very moment that Vin is at 0 and going up, what happens to VB1? VB1 is already at 0.7. And if VB1 at 0.7 and VE1 is at 0, that means VBE for the first transistor is already at 0.7 volts. Which means that T1 is turned on, which means that T1 conducts, which means that there would be a current through the load, through T1 and through RL. So from the very moment that Vin starts going up, from the very moment that it is slightly above 0, the V out will follow it. So as it goes up, Vin, V out will follow it too. So that crossover has disappeared. As soon as it drops a little bit below 0, what happens to this second transistor? Let's say that we are just slightly below 0. Between here and here, I have 0.7 volts. All right? And if this one is also at 0, that means between here and here, I also have 0.7 volts. And if I have 0.7 volts between the emitter and the base for a PNP, this transistor turns on. And if this transistor turns on, this one obviously will be off. Because now, as soon as this one drops below 0 volts, I don't have the 0.7, I don't have enough voltage between the base and the emitter. And this one turns on and that one turns off. And what happens is as soon as this one turns on, there's a current that flows through this transistor and comes down here. So there's a current in the opposite direction, which is the reason as soon as Vin goes negative, this one also goes negative. And notice that now there is no crossover distortion on V out. V out is pretty much follows Vin. When Vin goes up, V out goes up. When Vin comes in, all right, so there's no crossover distortion. And this is how we deal with crossover distortion. Right? So this is like a class B, except that it doesn't have crossover distortion. So this type of amplifier is simply known as a class AB amplifier. What does it mean, a class AB? It behaves like a class A in the sense that V out always follows Vin, no matter what it does. And it has the advantages of a class B, which means that the transistors do not conduct when there's no Vin. They only conduct when there's a Vin present. So it behaves like A in the fact that there's no crossover distortion, and it behaves like B in a sense that the transistors do not conduct unless there's a Vin present. Right? So that's the reason why we call it a class AB amplifier. So this one basically has some neat features of class A amplifiers and some neat features of class B amplifiers. Okay? The efficiency, by the way, for this one is pretty much like the efficiency of a class B. So the efficiency is roughly speaking about 50%. So it's as good as a class B, but it's way better than a class A. So it behaves like a class A in a sense that there's no distortion, there's no crossover distortion, but it has an efficiency as good as that of a class B amplifier, and that's the reason why we call this one class AB amplifier. And these are the only classes of amplifiers that you need to know a little bit about. All right? There are other classes available, by the way, quite a few of them, by the way, to be honest with you. There's C, there's G, there's T, there's S, there's I, but we have no business whatsoever with those. As far as I'm concerned, if you can tell the difference between a class A, class B, and a class AB, you're all set. Class B and class AB are always implemented with push-pull, which means you always use two transistors, an NPN and a PNP, and they are sitting one on top of the other one. And when one turns on, the other one turns on. Well, that's pretty much for this video. Thank you very much. And then I'll
see you in class, or I'll see you in another video that's going to come up very, very soon. Okay? All right.